All right, gang, here we go. This is for physics. This is Unit 6, Part 1. We're going to be talking about fluid mechanics. Specifically, in this video, we'll be talking about buoyant force. All right, so just a couple definitions of fluids. Remember, we've kind of talked about this before, but a fluid is anything that flows, okay, anything that flows. So that's liquids and gases. So all the stuff we're going to be talking about in this unit, primarily we're focusing on liquids and gases. Gases are kind of interesting ideas, but a lot of what we talk about is going to specifically talk about liquids. Now, gases, all this stuff definitely applies to gases, but because gases have different properties, a lot of the math we do will be primarily using liquids. All right, liquids have a definite. All this should be just common sense to you by now. If you don't know this stuff and you've made it to physics, I don't know how. Liquids have a definite volume, okay? So they have a specific volume, but they don't have a specific shape, okay? And gases do not have a definite volume. They fill whatever container you put them in, okay? What property of gas molecules allows them to fill any container? It's the fact that they are completely spread out, right? Gas molecules are all spread out, bouncing off each other. Remember the kinetic molecular theory from chemistry, okay? And then liquids, they're all a lot closer together down in whatever container you've put them in, all right? Density, all right? Density, new symbol for density. This is what physicists like to use for density, is this little, it's called rho, R-H-O, okay? It's the symbol for density. It's kind of like a curvy P, all right? And it's still mass over volume, all right? Now remember, in physics, our mass is always in kilograms, and our volume is always in liters or meters cubed. All right, those two ideas are equivalent to one another. All right, so those are our SI units for density, kilograms per meter cubed. This is going to probably throw you off a little bit, especially since in chemistry, since we deal with a lot smaller masses, our grams, when we talked about density in chemistry, primarily we talked about it in terms of grams per milliliter, okay? So, but a lot of times in this class, we'll be using density of water as 1,000 kilograms per meter cubed, or 1 times 10 to the third kilograms per meter cubed, okay? And then density of water is also 1 grams per centimeter cubed. And remember, this meters cubed is the same thing as liters, and centimeters cubed is the same thing as milliliters. All right, density depends on temperature, okay, and the pressure being applied. Now, this is kind of an interesting idea. As you increase temperature of a fluid, those molecules get more energy, right? So they're bouncing off each other harder. So the density of your system actually goes down. And we kind of saw this when we talked about thermodynamics. We talked about thermal expansion. Remember, we had the iron ball and the ring. They got them hotter and they got bigger, right? So as we increase temperature, our density will change. And the vast majority of molecules will get more dense with higher temperature and less dense with lower temperature. And then there's some notable exceptions, like water. We all know that water gets less dense as it freezes, and that's because of those hydrogen bonds forming those hexagonal structures, okay? And gases have that same tendency, but even more so. So then as temperature goes up, their density gets even less, even smaller at an exponential rate compared to liquids. Here's a list of different densities of common substances. We'll be referring to this several times. All right. Most of them kind of follow. You can kind of see that, one interesting thing, here's the density of steam. That's water at 100 degrees Celsius, okay, 0.598, and then fresh water is at, we already talked about that, 1,000. Notice that it's specifically defined at 4 degrees Celsius. This is the point at which water has the lowest density, okay, or the highest density, excuse me, okay, and then ice, here it's starting to get less dense again, all right. It's kind of interesting. All right. Anyway, so you got iron, mercury, gold, oxygen, so on and so forth. Okay. Buoyant force. So here we go with that new stuff for this unit. Okay. Buoyant force is defined as the upward force exerted by a fluid on an object. Okay. So no matter what fluid you're in, whether it be a liquid or a gas, there's always some sort of buoyant force, and this is the force of whatever you're submerged in. Okay, pushing back up on you. All right. So for example, I'm holding my hand out. Okay, gravity is pushing down on my hand, but at the same time, there's little molecules of atmosphere that are hitting the bottom of my hand, pushing me back up. And that is known as the buoyant force. Okay, now for the most part, In air, it doesn't really matter because almost everything is more dense than air, so everything wants to sink. Now, you know of some things that float in air, like helium, hot air balloons. Okay, those things are less dense. So the buoyant force is able to completely counteract the downward force of gravity pulling down on it. Okay, and then the same idea for things that are floating in water. If you put something that floats in water, you know that it floats because it's less dense, and it's less dense, meaning that the the reason that's important is because that means that the buoyant force due to the fluid that it's in is greater than, or can be equivalent to, the force of gravity pushing down on it. Okay, and so that really leads us to this idea, a couple of important things. All right, so the buoyant force is always opposite of the force of gravity. Okay, always opposite of the force. Gravity's, essentially we define gravity as going straight down, so the buoyant force is going straight up. So here's our force due to gravity. Okay, gravity, and then our buoyant force is always going to be opposite of that. So buoyant force of buoyant force, excuse me. All right, objects are always lighter in water. Always lighter in water. Even if they're not floating, they're still going to be lighter by some extent, and that extent is due to the buoyant force. Okay, and this leads us to the idea of Archimedes' principle. The buoyant force is equal to the weight of the fluid that's been displaced. All right, equal to the weight of the fluid that's been displaced. And really, the fluid that's been displaced, this is the volume, okay, of the object. Okay, and you savvy physics students out there might recognize the fact that, well, if we're talking about the volume of the object and we're talking about the buoyant force and then the force of gravity, we know that mass is important as well. And we just talked about density, mass over volume, right? And so this is why we spent a second talking about density, because all density plays a vitally important role when we're talking about the buoyant force. Okay, so here's the definition of the buoyant force. Okay, the buoyant force is equal to the force of gravity of the displaced fluid. Okay, and the force of gravity of the displaced fluid is simply the mass of the fluid being displaced times gravity, 9.81, acceleration due to gravity. All right. So buoyant force is equal to the weight of the fluid displaced. Okay, so we've got a raft here. Okay, and it's floating because the force due to gravity is completely counteracted by the buoyant force. Okay, those two are equal to one another. So the FB is equal to the force due to gravity. Okay, so therefore the overall force pulling down, the net force pulling on this raft is equal to 0. So F net equals 0, and that's essentially all there is. If your whatever you're talking about is floating in whatever it is, then you've reached the point where your net force is equal to 0. When I was a kid, I always thought it was really fun to get into the pool and then take a big breath of water, big breath of water. That's a problem. Don't do that. Okay, a big breath of air and then dive down, right? And you dive down to the bottom and your body automatically starts coming up. It's because you're less dense than the liquid, right? But then if you do it just right, you can breathe out some of that air and reach the point where you are exactly able to float right in the middle of the pool. You're not going down anymore, and you're also not going up. Okay, and when you've reached that point where you've let out just enough air that your densities of your body versus the liquid are equal to one another, okay, you've reached the point where your net force is equal to 0. Okay, now in the second example, it says, why does the second raft sink? Well, the second raft sinks because the force of gravity is greater than the buoyant force. And remember, the buoyant force is equal to the force or the weight of the water that's being displaced, or mF times g, and mF is the mass of the fluid being displaced. So that means essentially that the density, okay, of this object here is greater than the density of the liquid that it's in. And because of that, the force due to gravity is not fully counteracted by the buoyant force, or this MFG. We can also see that part of the reason it started sinking is because it started losing this air, which essentially made the volume of the raft go down, right? The volume of the raft went down, and because density is equal to mass over volume, as the volume goes down, the density goes up, okay? All right, so objects float, so the density, let's see, the density of the raft went up, and so the buoyant force went down. Okay, all right, objects float because the net force acting on them is 0. Buoyant force exactly balances the weight of the object. Okay, weight of the displaced fluid equals weight of the object. All right. So submerged objects, all right, this is a really, really important relationship here, okay? Submerged objects weigh less due to the buoyant force, and we can calculate what's called the apparent weight, okay? The apparent weight is the weight that you feel. So if you stick an object in water and you feel it get it lighter, that's the weight. The weight you feel is the apparent weight, okay? So the apparent weight can be 0 or it can have a whole range, okay? And to calculate the apparent weight, you take the weight minus the buoyant force, okay? So essentially, this also turns into the weight is the mass of the object, and we'll use O for object, times gravity, minus the buoyant force, which would be the mass of the fluid times gravity, okay? And we could pull gravities out, so it would be gravity times the mass of the object minus the mass of the fluid, all right? And this might be helpful later on. Who knows? Okay. The relationship between the weight, or the Fg, and the buoyant force can be determined with the relative densities of the fluid and the object. Okay, so we can take this idea here and do a little bit of rearranging and putting in formulas and densities and stuff, and we come up with this idea. Now, this idea is actually very important. Okay. Now, the force due to gravity on the object over the buoyant force is always equal in ratio to the density of the object. Okay, so this is object. Okay, over the fluid. Okay, so the force of gravity on the object divided by the buoyant force is always equal to the density of the object over the density of fluid. Okay, and we're going to refer to that several times in our practice problems here. Okay, so a bargain hunter purchases a gold crown at a flea market. After she gets home, she hangs the crown from a scale and finds its weight to be 7.84 newtons. She then weighs the crown while it is immersed in water and the scale reads 6.86 newtons. Is the crown made of pure gold? As explained. So essentially we can use density. Remember, density is an intensive property. Okay, and so that means we can use it to identify. Okay, so based on our table over here, remember this table, if we find that the density of the gold is equal to 19.3 times 10 to the third kilograms per meter cubed, then we know that the crown is gold. If it's not equal to that, we know it's not gold. All right, so we can find the density. So what do we have here? We find its weight. Okay, so this would be the force due to gravity. Okay, and then while it is immersed in water and the scale reads this. So this here, well, this is the apparent weight, right? So that's the apparent weight. Is the crown made of pure gold? Well, we know from the previous slide that the force due to gravity over the buoyant force, okay, is equal to the density of the object over the density of the fluid. Okay, so we want to find the density of the object, so we can multiply both sides by the density of the fluid. So that means that the density of the object is equal to the density of the fluid times the force due to gravity divided by the buoyant force. All right. So density of the fluid, well, it's just water. So the density of the fluid is 1.00 times 10 to the third kilograms per meters cubed. All right. The force due to gravity is the 7.84. Okay, 7.84 newtons. All right. Now we need the buoyant force. Well, for the buoyant force, we need to take remember, right over here, to get the buoyant force, we need to take the weight minus the apparent weight, and that'll give us the buoyant force. Okay, so the weight, 7.84 newtons, minus the apparent weight, 6.86 newtons. All right, so we plug all that in. So we get 1,000 times 7.84 divided by, divided by 7.84 minus 6.86. We get 8,000, all right, or 8.00 times 10 to the third kilograms per meter cubed. All right, so this is the density of that crown that the bargain hunter purchased, and obviously this is a lot lower than the expected value of gold, which is the 19.3, so therefore it is not made of pure gold. All right. Okay, a couple more practice problems. It says calculate the actual weight, the buoyant force, and the apparent weight of a 5 times 10 to the minus fifth meter cubed iron ball floating at rest, partially submerged in mercury. So this one's a little different because we've got mercury, okay, instead of instead of water. So we need the density of mercury to start. Let's just go ahead and get that. It's 13.6 times 10 to the third. Okay, 13.6 times 10 to the third kilograms per meter cubed. All right, so we got that right from the start. 13.6 times 10 to the third kilograms per meter cubed. All right, and it says calculate the actual weight, the buoyant force, and the apparent weight of this. So the actual weight, well, this is just the this would just be the force due to gravity. So this is the mass of the object times gravity. Well, the mass of the object, well, we have the volume, and we know it's made of iron, so we can find the mass by taking the volume times the density. Okay, so volume times of the object times the density of the object times gravity. Okay, so the volume of the object is 5.00 times 10 to the minus fifth kilograms times the density of the object. Well, it's iron, so we'll go over here. Iron is 7.86 times 10 to the third. Oops. Okay, 7.86 times 10 to the third. This was meters cubed. Okay, now this is in kilograms per meter cubed. All right, and then we take this times the force of gravity, or the acceleration due to gravity, acceleration meters per second squared. All right, so 5e to the negative third times 7.86 e. Shoot, dang, pushing the wrong buttons all over the place. 7.6 e to the third times 9.81. We get what did I screw up? Oh, I pushed in the wrong button. Here we go. All right. All right, so we get 3.85533 newtons. All right, 3 sig figs, so it'd be 3.86 newtons. All right, so that is the actual weight of the iron ball. Now we need the buoyant force. Okay, well, the buoyant force is equal to the apparent weight actual weight minus apparent weight, but we need to find the apparent weight anyway. But one trick it says is that the ball is floating at rest. Well, if the ball is floating at rest, this means that the apparent weight has to equal 0. Okay, so the apparent weight equals 0. All right, so that means that the buoyant force has to be equal to the force of gravity. So the buoyant force has to be equal to the force due to gravity, which is equal to 3.86 newtons. All right. All right, so there we get these three answers just the same. All right, and this says how much of the ball's volume is immersed in mercury. Now this you could do a really long ways, but I'm going to teach you a little bit of a trick. Okay, the ratio, okay, of the densities of the object to the fluid is going to be equal, or times 100 is equal to the percent immersed. Percent immersed. Percent of the volume immersed. Okay, so the ratio of the densities, well, the density of iron, okay, is 7.86 times 10 to the third, okay, and the density of the fluid is that 13.6 times 10 to the third, okay, and then we're going to multiply that by 100. All right, so we say 7.86 e to the third divided by 13.6 e to the third, all right, times 100. So that means 57.79% of our object's volume is submerged. Okay, so all we have to do is take that value, okay, so we take that 0.577941117 and multiply that by our volume, which is 5e to the negative fifth. And we get 2.89 times 10 to the minus fifth. Okay, so we take, so 2.89 times 10 to the minus fifth meters cubed is submerged. Okay, so we can just use that ratio to get that percentage relationship, and once we have that percentage relationship, we can just multiply it by the total volume. We can figure out exactly how much is submerged. And that's it for fluids and buoyant force. Not too hard, a little bit tricky with some of those units, some of those new equations, getting used to those ideas. Do your practice problems. Let me know if you have any questions. I'll see you on the flip side.